hang around people who forecast a lot, but the very first time I ever met Alan Moller was a day after there was a left-turning, splitting supercell that was fairly interesting. It was a mirror image storm, and it confused not only most chasers, but most of the weather service too, because all the warnings were tracking the storm heading to the northeast, and the storm was moving almost due north, and none of the radar reports were following where the storm was. We happened to stop in the Weather Service office the next day, and there's Al kind of doing a post-mortem on this, and just the excitement and passion about what happened the day before was overwhelming to most of us, because we were just thinking, this is awesome. And since then I've gotten to know Al, and he's got my respect for one of the best forecasters, and usually whatever Al says, unless I have really good reason to have brain freeze, I would accept it pretty much on that aspect. Al's been instrumental in providing a lot of severe weather forecast guides. He and Chuck had done the advanced spotter training, and he's also one of the integral parts of the latest storm watch video, which I think is the best spotter training video I've ever seen. It covers everything, and it covers storms from everywhere, from Alberta down to Florida. And so I now would like to give you Al Moller talking about the four-dimensional structure of thunderstorms. Do you have the slides? Okay. Let's turn the power on.
Okay, am I coming through on the sound all right? Paul called on Chuck and me to do sort of a session together in multi-scale analysis, and I suggested to let Chuck have the longer period of time to do something where you do some mesoanalysis, and I might do something on storm scale analysis. I'm probably going to refer to multi-scale analysis from time to time quite a bit, but not quite as much as Chuck had. Hopefully I'll reinforce a lot of the things that have been said so far by Chuck and Ron Przebalinski yesterday and Greg and so on, and maybe the people coming behind me will do the same. I can't tell you often enough that as Chuck said earlier, you've got to do a lot of analysis work if you want to understand weather. I have run into maybe one person I know of who I think is fully capable of looking at loops on screens and making really good forecasts from it. And this one gentleman had the advantage of doing a lot of hand analysis prior to this. I cannot look at a lot of loops of satellite and radar and so forth and make a forecast strictly from that. I mean, we just got AWIPS in our office in Fort Worth in the last month, and it's a wonderful system. There's a lot of good things you can do with it. But I still pull out the colors daily and analyze maps. If you want to learn about weather forecasting, it's simply the best way to do it. When I do, what I try to do is analyses of 850, 700, 500, and usually 250 millibars every shift. And once I've been on shift for a few days, I start pulling out my charts from the entire week and lining them up, and I start looking at what is happening and what sort of changes are occurring, what sort of continuity there is, and maybe more importantly, what sort of discontinuity there is from one set of analysis charts to the next. The other day I came in the office, I was not working, I was getting these slides together, and I caught some guys looking at the screen, and they're running loops of the surface data from hour to hour with satellite photography. That's great. And then they had the forecast from the Meso-Eta for isobars. Oof. I like the Meso-Eta, don't get me wrong there, but the first thing I noted was the pressures at given times are not matching the forecast from the Meso-Eta. But people were taking for granted that, hey, it's close enough. Well, that's not going to cut it. Without seeing who it was or anything much about it, the same crew was on May 5th, 1995, same couple of guys. and a tremendous storm waltzed right up to them, and our Sioux really saved her tails by, he was busy all day long, Mike Foster, but he came up and saw the squall line moving in from the west. You're going to see that in a few minutes. And he saw a storm developing ahead of the squall line, and he saw that the shears were high, looking a little bit of profiler data and some of the 88D data. And so he decided he'd better just sit down and watch the radar for a while. He got out some tremendous warnings. I had been on the midnight shift. I had put out a bad forecast. Paul, where are you? A bad forecast, which happens many times. And mesoscale things started becoming more obvious about 20 to 21Z. You weren't going to see it on any model. I'm still baffled by just quite what happened that day, but the data did show that something was happening late in the game. Anytime you're in the warm season and you're thinking convection, you've got to be analyzing data to see what's about to happen. What was about to happen that day was the world's worst hailstorm, dollar damage-wise. 20 deaths in the Dallas-Fort Worth area, not from hail, but from flash flooding and lightning, in addition to the hail that fell. A storm that caused about $2 billion with a B, dollars damage. I was miserably sick because I'd been on midnight shifts. SPC and I both went down the tubes with a severe weather outlook further south and west of our area, along where I thought a slow returning warm front was going to be down from Waco out towards Abilene. In my severe weather outlook, I outlined that area, and I said if there are any supercells today with a risk of large hail, very damaging winds, and maybe an isolated tornado, it was going to be in the southwestern part of our area, and it ended up right on top of us. The guys in the day shift didn't catch it. And they, when the severe weather outlook went out later, they never updated anything. So we were caught pretty much with our pants down, but we were saved by our Sioux who got on the radar and put out some excellent warnings. Anyway, I'd better get into this. The thunderstorm spectrum. I put this first slide up, and lo and behold, one of the comments Chuck made last night, which made me think, he said, it's not really a spectrum. Well, here we've got it drawn as a spectrum. And he's right. Storms tend to clump in different areas. I mean, when we have supercells, it's in many cases pretty definitive what you're dealing with. Squall lines are fairly definitive. Clusters of storms and single cell and so on, but they tend to clump rather than being a real continuum like the electromagnetic spectrum. However, and we could punch holes in this type of classification scheme all day long. There are more problems with this scheme than there are solutions from it, I think. But there's nothing there to replace it yet. Eventually there will be. Most of the stuff I'm going to tell you this morning will change in time as our thinking changes and we see more of these storms. Single cell storms, multi-cell storms, squall lines, and supercells. The modelers have suggested a better way to look at a storm spectrum would be supercells and then everything else, consisting of ordinary cells. So, maybe that's the best way to look at it. Ordinary cells and supercells. The difference being there's a lot of rotation in the updrafts of the supercells. You have a mesocyclone on the order of about 30 knot rotational velocity over 3 or 4 kilometers, something like that. What is it? 10 to the minus 2 per second vorticity? Chuck, are you around? Is that about correct? Yeah. Okay. So, supercells are very important because of the rotation in the updraft. Other storms can be either severe, but most of the time they're non-severe. I'm going to move on if I can figure out what I'm doing. The two main ingredients that help the atmosphere determine what sort of storms are going to develop: instability and vertical wind shear above a given point. Now, I've thrown on 3 stability charts from April 1994, April 25th, from Stephenville. The sounding site is now in Fort Worth. These soundings are kind of interesting, though, because it pretty much exemplifies something Chuck has talked about, and that is that what a shortwave trough or an upper level disturbance, whatever you're going to call it, what it generally does is it destabilizes the atmosphere and sets the stage for convection. Now, we have 3 soundings, one at 12Z, one at 18Z, and that was ordered up by SPC, and one at 00Z. In the morning at 12Z, we had a very strong inversion, capping inversion, and in essence, there are 2 air masses we're looking at. This is a Gulf air mass down low, and this is what some people lately have been calling an EML up here, an elevated mixed layer, where essentially you've got a very unstable lapse rate, a little bit of a glitch in it in there, but very sharp lapse rate, and it's a very dry lapse rate. Chuck and others have shown that this generally is air that is coming off the southern, off of the southern part of the Rockies or out of Old Mexico, up on the Mexican plateau in the mountain area. And you've warmed the low levels, which is at 850 to 700 millibars, but you still have cool air aloft, and it's very dry and very unstable. We've got a strong capping inversion between these two air masses. Now, let's watch what happens to these two air masses during the day. From 12Z to 18Z, the moist layer is getting deeper, and the moisture is getting more plentiful. It's getting richer and deeper. One thing, I'm going to go back again. Let's look at the wind field as well. In the morning, the wind field shows a low-level jet, a real bad-looking weakness for, say, supercell storms in here, where we go from 25 to 30 back down to 10 and 15 knot winds. Then we increase them again to some higher speeds above that. Not a whole lot of shear, and the weakness in the wind field there, problematic, of course, for supercells. At 18Z, the wind field still doesn't show much directional turning, but the winds in that weakness are starting to increase. The moisture is getting deeper, and the inversion is decreasing. So this is indicative of the slow lift. The entire sounding is being lifted slowly, and we're weakening the cap, destabilizing the atmosphere. Here's 00Z. The cap is gone. The moisture is quite deep. And look at the wind profile from south-southeast on up to the west-southwest. The winds have gotten a lot stronger, and we've got the kind of low-level shear that may favor supercells, and that's what happened on this day. You'll see the radar of this shortly. We may want to say that in the summertime, you generally have weaker winds aloft, especially in the southern and central parts of the U.S. And for the most part, the convection, at least apparently from what we can see, is rather unorganized. You don't favor new cell development on a certain flank of the storm that keeps that storm regenerating. You do have a cell go straight up and the rain falls back through it, and there's outflow and additional cells and so on. In the past, we've often called those single cell storms. Chuck has pointed out, though, that it's a series of bubbles inside of every one of those cells. So maybe, although it is one main updraft area, maybe the fact that there are a series of pulses in it means there's no real thing in the atmosphere as a single cell storm. Maybe all storms are actually, quote-unquote, multicellular. When you start to get stronger winds aloft and more shear, you get stronger storms. Notice here with multicells and squall lines, in many cases you do seem to see a weakness above the low-level jet. With supercells, you usually see continuing strengthening of the winds and a lot of turning concentrated down fairly low. It's not necessarily always a southeast wind becoming southwest. It might be an east-northeast wind becoming due south. That's what they had at Edmonton, Canada in 1987 prior to that tornado. A lot of turning, a lot of speed shear. We convert these into photographs. I'm not going to try to give a seminar on photographs, except that you need to learn how to do them and how to look at them. Chuck's got an excellent paper in that. I may briefly show you some photographs from some of the other storm types, but generally that's the surface wind vector, the 850 wind vector, and so forth, and the lines connecting them. That is the shear vector. And your shear vector here is like this, pointing to the east, and the shear vector from 500 and so on. This is the storm motion vector here, and the greater the area from here on up, from here on up to 4,000 or 5,000 feet or so, maybe 2 or 3 kilometers, the larger that area in there, the greater the storm relative helicity, the greater the potential for storm rotation in the updraft. So-called single-cell storms, this is looking to the north. The downwind anvil indicates the storm generally will be moving from left to right. Here's the updraft area, and the rainy downdraft is probably offset from this somewhat because there's a little bit of strength to the winds aloft, although the shears were not terribly strong on this given day. I want to caution you about something. Storms move generally because of two major factors. One is the advection of this cloud by the winds, the advection of the air by the winds, and the other factor is if the cloud is developing on a preferred flank, how fast that development, that flanking development is. In many cases, when you have a supercell and it's developing hard to the south along its flanking line, that's when the storm deviates and turns more to the right and slows down a little bit, because you've got to add those two the motion vector and the cell development vector together to come up with how the storm is going to be moving. Okay, this is a summer type of an organized storm. And in essence, your updraft develops straight up and down, and the rain, and if there's any hail, collapses right back onto the updraft, and the storm dies very quickly. The difference between the upper and the lower is this is an ordinary, organized storm, unorganized storm. This is a severe unorganized summer type storm. And notice that the high reflectivities extend up well past 6 to 9 and maybe 10 or 12 kilometers with the severe storm. It's hard to warn for that type of storm because you don't have much lead time, but you will see a lot of strong reflectivity aloft at higher levels than you will with the ordinary type of non-severe storm. That's a gross generality too. Okay, let's see. Did I skip a slide? I'll look at this one first. Sometimes you get out of this type of cell these small and usually weak tornadoes, and some people have called them land spouts. Chuck has said we ought to call a tornado, and I agree with him. I don't like to try, especially in talking to spotters, I don't like to get them trying to determine if they're looking at a land spout, or water spout, a tornado, or whatever. If they see a tornado is good enough for the reporting. But what's going on is that there's a pre-existing boundary with a high amount of vertical vorticity. Towering cumulus comes across that, and it pulls up and stretches that low-level vorticity, that pre-existing vertical vorticity. And the stretching sometimes results in that. The stretching in the updraft sometimes results in a tornado developing. I'll go back to that last slide briefly, if I can punch the right button. I can't see the ground there. I apologize for that. But this is a fairly shallow cumulonimbus cloud. In July in Fort Worth, there was very little wind speed aloft, and there's one of these little non-supercell tornadoes called, some people call a land spout. Now once we start getting stronger shears, and in many cases stronger instability, we get stronger storms and longer lasting storms. Multicell cluster storms. These cells, a storm cell is the updraft and that updraft's rainy downdraft. So a storm, if it has more than one cell in it, we call it multicell. One of the problems the modelers have had is they haven't had an easy time, and I don't think anybody has yet modeled what I would call a classic multicell storm. Something I think is important is a lot of supercells come out of a complex like this. Not all of these produce supercells, not by a long shot, but supercells usually start like this. We have watched several multicell storms develop in close to the radar in Fort Worth in the last couple of years, and what we have seen is each one of these towers on a day with a true, what I would call a classic multicell storm, each one of the towers has some rotation in it, enough for the velocity display to register on the Doppler. Maybe 15 knots, something like that, maybe 20 knots. They're a little bit more distinct than a supercell where, well, I'll get to that in a minute. These are a little bit more distinctive in that you see different updrafts, and with supercells sometimes you have, with the flanking line, more of smooth inflow from the flank into the supercell updraft, whereas here you have more of a discontinuous look to the updrafts in a multicell storm. It might be that a multicell storm is really the initialization of a supercell, but in a lot of cases maybe it's never going to get there. I'm starting to think that maybe the reason they can't model one is because these are incipient supercells and most of them never make it to that 30-knot rotation of a supercell. I don't know. I don't think these are quite as common as I used to think. It seems like there are other modes of multicell that appear a lot more often than this type of thing here. We're looking north. Here's heavy rain falling beneath the higher tops, which are glaciating. This is the flanking line, and there's rain-free base beneath that. This is where the new cell development occurs on the right flank, with cell dissipation occurring on the left, or usually the north flank of the storm. In many cases, we have a hodograph which does show shear, and this is the old one from Chisholm and Rennick in Canada in the 1970s. And in a lot of cases, your multicell storm will move fairly close to the hodograph. In this case, the motion's a little bit off of it. This is a kind of hodograph that not only you get multicell storms like the one we're looking at, you often get splitting storms, and sometimes you'll get splitting storms where the right mover is a supercell and the left mover is an anticyclonic supercell. The key is for them to move well off of the hodograph, one up here, the left mover, and the right mover well off the hodograph on the cyclonic side. And then you may get the kind of rotation to get the supercell structure. It's kind of a chicken and egg question, which happens first. Time equals 0, time equals 0 plus 10, and 0 plus 20 for a multicell storm. Cell 2 is about to drop its heaviest precip, which a few minutes later is falling to the earth as cell 2 begins dissipating. Cell 3 then, there's a little bit of overhang in the storm, maybe some severe weather. And a few minutes later, the heaviest burst from cell 3 is falling to the ground as cells 4 and 5 are developing aloft. Now again, the cloud parcels may be blown from left to right here, but because of the new development on the right flank, the storm probably will move a little more to the right of the mean flow than usual. It may decelerate a little bit. Squall lines. They're multicellular. That's why we've given it a somewhat awkward name. They're multicell line storms. Squall line's good enough. Why do we see these smooth tiered clouds like this? This is some sort of shelf cloud structure. That's where the outflow commences. What's probably going on is the gust front is lifting air forcibly, which is stable. And with that stable lift, we see these smooth layers, and then above that, you're probably going to see cumulonimbus clouds if you could get above the cloud deck and look at it, which we cannot from beneath it at this point. We're looking west, and the squall line is approaching us from the west, moving east. Here's a hodograph that was taken from an average of squall lines. Quite a bit of shear, a little bit more curvature in the low levels than the multicell storm. I'm not sure if I'd put a lot of faith in that. Sometimes I'm not sure what to make of these averaged photographs. As seen from above, a squall line advancing generally eastward. The updrafts are on the leading flank, as we see in the cross section from A to B here. The heaviest precipitation is adjacent to the updraft area in just about every thunderstorm you'll encounter. In the multicell storm we just looked at, the updrafts were on the rear flank, and the heaviest precipitation was shaded towards the rear flank. In this storm complex, with the updrafts on the leading flank, the heaviest precipitation is adjacent to it, right on the leading edge of the storm. Then the precipitation tapers off in time. The greatest risk of severe weather is on the leading flank, usually in the form of wind gust, maybe hail, and in some cases tornadoes. I think now it's safe to say that we're now seeing more tornadoes with elements like this than we used to think existed. I'm not trying to say every squall line is going to produce tornadoes. Most of them do not. But there are more little bitty nooks and crannies where small, brief tornadoes can occur. Sometimes we see them on radar, sometimes we don't. We're going to look at some slides on radar of those shortly. But this is a fairly quintessential squall line. And nature likes to turn the atmosphere over. This is a very good way for the atmosphere to turn over the instability and stabilize the atmosphere, as Chuck was discussing earlier. Okay, just very briefly, talking about the gust front and the relation of the gust front and vertical wind shear. Here is a thunderstorm without vertical wind shear and without a cold pool beneath it, and it develops pretty much vertically, as we saw with those typical summer storms. Here is a storm without much strong wind aloft, but it's got a good cold pool underneath it, and what we see is because of the cold pool pushing outward, we get a tilt of the cloud back towards the cooler air back to the west, above the cooler air. Ron Presblinski showed a lot of this last night. In this situation here, there's no cold pool yet, but vertical wind shear, stronger winds aloft, have resulted in a cloud tilting down shear. So you put the two together, a cold pool and a little bit of vertical wind shear, and in many cases they balance out. That's especially true and strong squall lines with a better chance of severe weather. Of course, this may go to this, as Ron was showing, towards the dissipating stages. But then again, it may go back to this again if it regenerates. Hand-drawn things, and some of the people have been emailing lately. Jim Ledoux and Rich Thompson and Roger Edwards and others have been suggesting that when you have here is a line of convergence. Well, I've drawn a dry line. These are not low-level winds. Those are mid-level winds. So you have southeast winds coming in like this and west winds back there. And this is the area where the storms are going to develop. Now, when the storm relative mid-level winds are blowing parallel to that line the convection develops on, you're more likely with this updraft to spill its rain onto updraft 2. And updraft 2's precip spills on updraft 3, and so on. And you quickly develop a squall line in this situation because you're raining into all of the downwind updrafts. On the other hand, if you have the mid-level flow blowing parallel to the boundary the storms are developing on, a lot of the precip is blown out ahead, and you don't get as rapid a development of a squall line if one indeed is going to occur. That might give the storms more time to become severe and produce all sorts of severe weather. Now, you can get, as in the last case with the squall line, you can get severe weather with this, but there was so much interference with the updrafts, probably not as much as in this case, where the storms may remain isolated for a longer period of time. Of course, our bow echo, which I don't need to detail much, Ron did an excellent discussion of this last night. Here is a bow echo. This was near Silverton, Texas, looking off to the north. And notice the curvature. You can see it curving back and then curving back in here. That's the bow right there. And indeed, I was with sweaty palms at this time trying to outrace this storm off to the east, and the winds behind it, the reports I was hearing were winds of above 80 miles an hour with golf ball hail. And I did not want to mess with that. A very violent thunderstorm. Let's get to supercells. Let's look at this cloud for just a minute. This is the king of them all. This isn't a mini supercell. This is a big supercell. Looking off to the east from about 30 miles. This is the main updraft area, the main cumulonimbus cloud, the downwind anvil. Heavy precipitation because of the winds aloft falls a little bit downwind of the base of the updraft area. This is the flanking line. This is an area if it's a true classic multicell storm, usually you'll have discrete updrafts developing, separate updrafts, each becoming a new storm cell. Many times with supercells, these areas kind of smoothly merge into the main cumulonimbus cloud, sort of a feeder line of smaller clouds rather than discrete elements separate like they are in a multicell storm. In a paper that's years old now, but still an excellent paper by Foote and Frank, they looked at what they called strong evolution storms and weak evolution storms. These are supercells. And that's what I was just pointing out. Along the flank, you have kind of a smooth transition with clouds exploding up into the main updraft area, whereas you have new cells developing in the multicell storm. In between, they had well, this was strong evolution, this was quasi-steady, and the center was weak evolution. And I think that we've got enough evidence to show that what they called a hybrid supercell multicell, in many cases, is what we call an HP supercell. And you've got something in between the strong evolution and the quasi-steady. It's not really steady. We know more about that now. Typical hodograph or supercell storms, a lot of area in there, more storm relative helicity. I've got to move on. This is pretty important right here. If you all haven't studied the vorticity equation, you will be at some point. The time rate of change of absolute vorticity equals the divergence term, and that usually manifests itself with thunderstorms in the form of stretching within an updraft or shrinking within a downdraft. So you enhance the vorticity by stretching it, you decrease it by shrinking it. The tilting term, which is where you're tilting from one axis to another. Vertical wind shear, if you can see my hands coming in towards a storm, winds from different directions at different speeds. You tend to want to get a rolling pipeline of air, although it's not really rolling in the horizontal because it's a fluid, it's not a solid. But when you tilt that up into a different plane, which is the updraft, it does actually rotate. And that's where the rotation of the supercell comes from. The solenoid term is baroclinic vorticity generation. This is a gross simplification, but generally cool air flows under warm air because of its density. And again, you can see you're developing some, with my hands, you're developing some horizontal vorticity, and if you tilt that into an updraft, you get another source of vorticity within a cloud. So it's pretty well known that this plus this is what leads to the development of the mid-level mesocyclone. At some point after that, prior to really violent weather in low levels such as tornadoes, you usually develop a low-level mesocyclone, and then at some point after that, a tornado. But now we're seeing some storms where the whole process occurs very quickly, apparently from the bottom up, but almost all at once you see rotation developing, strong rotation, and quickly after that, a tornado. And I'm going to skip friction right now. It's important, but I don't have much time. Mesocyclone is a persistent region of rotation several miles across and through deep layer of a thunderstorm. It usually starts out in the updraft area, and it more or less shifts into the interface of the storm's updraft and downdraft areas. If you've never read the Lemon and Doswell paper from 1979, you've got to leave here and make that a top priority to read that paper. It's almost 20 years old, but most of that information still holds. It's a very important paper. Let's continue. Over 90% produce severe weather. Less than 30% produce tornadoes. This seems to get lower and lower every year. We're seeing a lot more rotating storms than we first realized. There's a high failure mode, fortunately, in supercells producing tornadoes. So many of them, most of them, do not produce tornadoes. Mesocyclones produce a substantial fraction of the worst downburst, and I'm talking about lower echelon tornado intensity winds and downburst. And we made this slide about 5 or 6 years ago. Occasionally, mesocyclones produce 4 to 7 inches of rain within a 1-hour period, and it's that kind of storm in Dallas that killed 19 people on May 5th, 1995. You can have, because of the tremendous burst and the tremendous rainfall rates, some exceedingly severe and quick-hitting flash flooding from a storm like that. Mesocyclones produce almost all strong and violent tornadoes and many of the weak ones as well, and they produce almost all giant hailstones 2 inches in diameter or greater. I still want to see somebody give me proof positive of, say, baseball hail coming from a non-mesocyclonic storm. It may have existed at some point, but I don't know about it. Here is our quintessential model of a classic supercell. Most of the precipitation thrown out ahead of the storm by the winds aloft. A very popular tale that is still making the rounds. A very common misconception is that hail is blown out of the top of the storm a long ways downwind. That's not true at all. The largest and heaviest particles fall back first, and that's the largest hail, which falls very close to the updraft. Then smaller hail and heavy rain, and further from the storm, no hail and light to moderate rain. So there is a size sorting of precipitation, with the heaviest stuff falling adjacent to the updraft area. And if you chase storms actively, or if you spot them, beware of this area in here, which in a classic supercell may look to be rain-free. Sometimes isolated chunks of giant hail fall very close to the wall cloud. The warm air cools and saturates at this level. The rotating updraft is so strong in the supercell that it starts pulling some of the rain-cooled air out of this area, and that rain-cooled air has higher humidity, and when it's yanked off the ground, it saturates earlier, and it produces the tail and the wall cloud below the cloud base of the so-called rain-free base. The same kind of cooling from the rain produces the shelf and roll clouds and those other structures seen under, and scud clouds, all of those structures seen under the base of the storm. In some cases, we've watched supercell storms produce large, low-hanging wall clouds, and then they seem to weaken. Maybe at that point the storm is trying to ingest too much rain-cooled air. Maybe there's a balance. Most of the air is warm air, but there's some cool air, and that's right at the boundary where the mesocyclone is in this area. And you can see that it's pretty much vertical from the wall cloud to the overshooting top of the cloud. The long part of the anvil extends downstream to the right. Often you see a very strong-looking anvil on the backside, an anvil overhang, very sharp edges, very cumuliform edges as well in many cases. The flanking line, and so on. I love this diagram. It's one Browning did many years ago. Here's the track of a supercell. Here's the track of another supercell. They developed along a warm front, as many supercells do along boundaries. These are tornado tracks. There's 3 of them there. There's one here and another one there. And you can see the giant hail falls near the tornadoes, in most cases, and just immediately north of it. That's near where that wall cloud is in that diagram we just looked at. So be wary of driving underneath a wall cloud, because bad stuff often happens. As seen from above, the hook echo, the mesocyclone here, and a wave in the gust front. And again, the heaviest hailstones, the largest hailstones falling adjacent to the updraft area. This is the Lancaster storm event. That's the evening of the soundings we looked at to start off the discussion. Here is the Lancaster storm. It's about to produce the Lancaster tornado, which was a violent F4 tornado. That's your hook. And on its gust front, which is this little guy right back here leading up into that, there's another supercell right on the tail end. Supercell storms are probably most important when they're seen traveling along boundaries, and Eric's going to talk about that. Here is the tornado vortex signature. It's maximum inbound to the radar, which is inflow in this case. The radar's off to the left, and maximum outbound or outflow. Gate to gate, this is the lowest scan level, and that's at about 2,300 feet, I think. That is a tornado vortex signature, and there was a violent tornado on the ground at that point. A larger scale view a little bit earlier, not only was the Fort Worth storm in the boundary of the Lancaster storm, but the Lancaster storm was on the boundary of this earlier convection in the afternoon. This is where that analysis comes in. In trying to get a subjective gauge of mesocyclone strength, we use a diagram kind of like the one you see here. That's 30 knots right there, and that's about the lower echelon for a mesocyclone. But you can see that all of this is range dependent because of beam width spreading, as Greg was talking about last night. So it's harder to sample a mesocyclone at great range out near the edge of the velocity range at 125 nautical miles. It's easier to see it in a little bit closer, except when it's right in the cone of silence. Okay, what I'm going to show you is progression of a storm from a fairly weak updraft in a sheared environment to a strong updraft in a sheared environment. I'm not going to try to tell you that every supercell is going to do this type of thing, this type of act as it forms. Some of these low-top supercells and even some of these highly sheared supercells Greg was talking about pretty much defy this. But the upper end supercells usually start out as a highly tilted updraft, as we see here, and then downstream there's a rainfall out area there, and the highest top is directly above the core of the storm. There's a lot of tilt to the updraft. This is a weaker updraft in a sheared environment, and that's the top in this plan view directly above kind of a bullseye looking precipitation pattern is seen on radar. The storm gets stronger, the updraft gets more erect. In essence, the updraft speed within the supercell probably at least doubles because of the strong rotation. This is shown in the four-dimensional models on the Cray supercomputer. So we have a more vertical updraft than we had earlier. It's a stronger one, and we'll show you what spotters would see in just a minute. Beneath it, we call that the weak echo region, strong inflow coming in and up. This is an updraft which may be rotating, it may not be, but it definitely is a storm that's becoming severe. The top shifts from being over the core at the ground to being over the right flank, and often it shifts from the core of the storm towards the gradient area. And the core, even the core of the storm is shifted towards the southwest side, and notice the very strong gradient, which is what you often see on the updraft flank of the storm. So even if you don't scan a storm in 3 dimensions, once you see that gradient tightening up, you can suspect there's probably that's probably the location of the updraft, but you should use 3D radar to confirm it, and this overhang does confirm that. This is where a storm undoubtedly is becoming a supercell. Not all supercells, especially some of the lower end ones, have B-weirs or bounded weak echo regions, completely surrounded by strong echo. But I would say that virtually every time you have a B-weir, it is associated with a supercell. Notice the highest top is shifted completely off of the storm echo. into the area just ahead of the hook, and that is the mesocyclonic updraft. And that is a visual or radar indication of it there. High-speed jet of air rising up. Precip doesn't even have time to develop till it gets well above this area, and then it spreads out in the overhang above the B weir. What does this look like visually? Number one, highly tilted storm with a flank. There's one updraft that's starting to tower a little bit more vertically. Storm's not especially strong now, probably heavy rain and some small hail. Then one of those towers, probably the one we were looking at in the flank, becomes more vertical, much more explosive looking, and we see some striations in here suggestive of rotation. This was a supercell storm developing. It was going to the severe stage and the supercell stage. It's quite a difference from start to finish there. What does this look like from underneath cloud base? Well, in the weaker stage, looking west, here's a precipitation area downwind to the northeast of the updraft base. Things are not extremely well organized at this time. Don't think I'm trying to tell you, if you see something exactly like this, that it means it's a non-severe storm. Looks can be deceiving. But generally speaking, things start to sharpen up a bit in the next stage when we're going towards a severe storm. The rain-free base becomes considerably darker because of the higher tops directly above it. The rain area becomes sharper in appearance with heavier precipitation. And when you see this kind of appearance and you know you've got a lot of shear and instability, it's time to think about not driving into that part of the storm right there. And then this is a majestic storm from the underside. It's got everything. Tremendous B weir, mesocyclone. It's about to produce a tornado looking west. The radar vault, which is the B weir, is up in here. The visual vault that spotters or chasers sometimes refer to is the northern edge of the updraft area in there. You can see rain wrapping around a wall cloud, and again it's moving over Archer City, Texas. They were blowing the sirens. Luckily for them, the tornado waited till it got over here east of town. Going back temporarily to the squall line to look at the 3D structure. This is a squall line in northwest Oklahoma last year, and it's moving towards us to the southeast. And now we're looking down to the southwest part of the line. They not only build on the leading edge, they often build southward with time. And again, you'll have the wind shift with the onset or the approach of that shelf-type cloud. Just before it arrives, you'll have the onset of some straight-line winds that might be damaging. They might not be damaging. But since this is a leading-edge phenomena in a cross-section from A to B, and this is from Les Lemon's Tech Memo, you look for overhang on the front flank. Usually with a classic supercell, usually it's on the right flank. But in this case, on the front flank, and you're going to see a little bit sharper gradient in the plan view in the low-level reflectivities. And if a storm does become severe, you're often going to see something like this on the leading flank. This is the rain area. This is the base of the updraft and the top of the updraft. So there's a weak echo region that's more or less capped off by very high reflectivities. And Ron Presblinski's figure again with the bow echo. This is from one of Ron's papers. And the maximum echo top out in the front edge. There's your echo overhang in the plan view as seen from above looking down. And his weak echo channel often indicative of very strong winds. Okay, is this scientifically done? No. It's kind of guesswork. This is the supercell we were looking at off to the east, and an updraft in this area. That's the B weir, and very strongly capped with high reflectivities above that. The extremely large hail is going to fall in this area, and smaller and smaller droplets as you get further away from the core of the updraft. And I did that diagram up after seeing this diagram for many years. This is one of Browning's figures, and this is interesting. It shows more or less the trajectories of hailstones. The parcels are rising, small raindrops, and some small hail forms, and there's a sort of a modified what's the word I'm looking for? Recycling. Thank you, Chuck. Modified recycling. They used to think it went all the way up and down the storm, but there may be some recycling. But for the most part, that hailstone is riding on the upper part of the B weir and spending quite a bit of time there as it finally comes down to the ground over in this area. So this gives you some idea of what's going on with hail formation. And when you have a 100-mile-an-hour updraft, and that hailstone percolating on the top of it, that's where you get a lot of growth to that hailstone. You've got to have the intense updraft to help hold the hail aloft as it's forming. From the bottom up, here is our classic supercell. And one of the reasons I show this is at range, you're not going to see these guys down here. Here's your B weir and B weir, heavy echo north of it. And directly above the B weir, there's very high reflectivities. If you're looking at a storm, say 125 miles away to 250 miles away, often a supercell will be a large storm, larger than neighboring storms that are non-supercells, and it will have more intensity to it. So you can look at a storm at a great distance and beyond the velocity range. And what can you do? You can surmise where the strongest storms are. They may be supercells, so you dial up another radar closer to it, and you alert spotters that they may be dealing with a very severe storm. And you're going to have to get input from spotters as to what's going on out there. Of course, you need the spotters in here too. The radar won't tell you for sure a tornado is occurring. This is the Red Rock, Oklahoma storm. In the low levels, there's the hook echo. A little bit above that, there's your B weir. Directly out in front of the hook, right in there, that very marked B weir. And that's the upper part of the B weir where it's beginning to be capped off with echo. But notice that the largest part of the storm aloft is south of where the greatest reflectivities are in the lowest elevation cut. Well, that's not a surprise to us now. There's a lot of overhang in here, and it's going to be very dark as seen by spotters in this area with a dark rain-free base and quite probably a wall cloud. In this case, a full-fledged tornado. Your echo top is directly above the B weir, which is directly above the mesocyclone. Yeah, it is part of the mesocyclone. Sorry, it's directly above this. This is what I was getting at. Let's race ahead. That. Okay, back to the velocity. Maybe. There we go. In the low levels, we see pure rotation. A little bit higher, basically rotation. And above that, we see divergent rotation. That air is doing this air is doing this. So it's becoming divergent, and then up on top, there's no rotation left, just pure divergence with inbound to the radar and outbound. Pretty much the profile you would see from the surface on up. Now, this was the storm as we approached it before the tornado we just saw. Sorry, things are out of order. I was chasing with an amateur radio operator from Dallas who's become an excellent chaser, Sam Barraclough, and we were watching this back-sheared anvil and the main cumulonimbus top, and what was interesting was the rapidity of growth on the flanking line. You'll probably not see any stronger convective formation, convective growth than on the right flank of a supercell. There's a strong mid-level mesocyclone in here, and that is causing dynamic lift. Again, that's what essentially doubles the rate of the updraft speed, and you often see that with a storm like this in the storm ingesting cloud elements along the flank, and these rise very rapidly. This tower here, about 60 to 90 seconds later, let's look at the difference. It's all the way up. Very fast. It's gone all the way through the anvil, and more turrets are rising up. Again, these don't look like the really discrete different cellular elements that a multicell produces, but you can see they're being ingested into the updraft very quickly. Now, watching the rate of that updraft growth, I said, and this, for once I was right, I said, we're going to see a tornado out of that. And this is what we saw a little later on. Splitting storms. Here is a storm that split in the Wichita Falls area, and that was the 1964 Wichita Falls tornadic storm. Left mover, and it split again with a left mover and a right mover. Here's a storm that formed, and it split with a right mover and a left mover. There were several tornadoes. The worst was with this storm in Wichita Falls. Let's look at these left movers for just a minute. This is from Lemon's Tech memo. Here are splitting storms, not the same situation. This is later than that. And up here we see storms with overhang on the right flank. Those are either strong multicell or supercell storms. That's probably a supercell. And here again, there was strong overhang on the right flank. And again, you can see the tightest gradient is also on that flank. That's where the updraft is, and the overhang, and the highest top. Those are severe storms. Here's a left mover moving off of a right mover. You can't see the bottom of it, but it's got the same thing on its right flank as these guys do. But the left mover has overhang on the left flank. Its updraft is up here on the north side of the storm, and again, that's where the tightest gradient is. And notice some curvature. That's an anticyclonic storm in many cases, with anticyclonic rotation. What do these storms look like? This is looking south from my house one day. A supercell out of the picture to the right has gone down towards Waco and tornadoed. This is a left mover that split off of it, looking south. The main tower and the highest top is on the northwest side of the storm, with a flanking line on the north side of the storm. It's kind of a mirror image of the supercell, but instead of the flank being on the south side, it's on the north side. The storm is building north with time, and essentially because of that, moving more northward or to the left. Here is an anticyclonic storm on the underside, looking northwest, and this storm was moving towards the northeast. It's a rather small tower in the low levels. Notice it's flared, and frequently you see that with small rotating storms. And under the base, this is one of the few left movers I've seen that actually had anticyclonic curvature. Now, to me, something still looks kind of strange about that, but it definitely had some anticyclonic curvature. I was getting hail up to about marble size, or maybe some dimes. Roger, it depends on whether a warning's out or not. And there were larger hailstones falling closer to the cloud. There were golf balls falling in this area. You can see right through much of the precipitation area. It's a small precip area and a small updraft, but there's rotation and a lot of strength and large hail falling. There was a tornadic storm south of that one. This is another anticyclonic storm on the north flank looking south. And again, the top and those knuckles and the underside of the anvil on the north side of the storm rather than on the south side. This is the same storm. This is the main updraft and its flank. And I think this is probably what is showing up as overhang on radar. See how precipitation streamers are being recycled into the updraft area or close to it. So that's probably what would show up as anvil overhang, or radar overhang rather, on the north side of the storm. This is the same storm looking off to the east, and the flanking line back out on the northwest side, and there's kind of some sort of modified beaver's tail up in the mid-levels indicating inflow on the north side of the storm. Peekaboo, what do you think that is? Anybody?
Right.
Yes, that's the right mover. This is the left mover, that's the right mover. And after dark, this is the right mover, looking east-northeast. Flanking line in the moonlight, main cumulonimbus, wall cloud, and heavy rain area behind it. There was a tornado occurring from that wall cloud at this time. And it was a weak tornado, just blew out the glass of a Dairy Queen, but it was enough to injure 13 people. Supercell variations. The important thing is, and what I thought about doing, and I ran out of time, was getting a Mr. and Mrs. Potato Head set and dressing them up differently and showing them how different Mr. and Mrs. Potato Head can look. But you can't stop the fact that it's Mr. and Mrs. Potato Head. A supercell is a supercell. They have different garments, maybe. People are probably making a little bit too much out of, well, this is an HP supercell, so that means no tornadoes. Or it's an LP supercell, it means big hail, no tornadoes. If it's a supercell, you've got to watch it if you're a spotter. An HP supercell usually has more heavy rainfall within the storm system. It's often a large storm, and according to our loose definition, it has precipitation in the mesocyclone as well. So it's harder for spotters to look at a storm like this. We can see that right off the bat. We've got the wall cloud drawn rather clearly here, but it's often very difficult to see with all the precipitation curtains wrapping around it. As seen from above with radar, often there's very high reflectivities wrapping around the back side of the storm. So in essence, we go from a supercell updraft in the right rear flank to a supercell updraft in the right forward flank, often on the southeast side of the storm, but it might be the east or the northeast side of the storm. But there's a lot of precip wrapping around the back flank. This is the wave gust front, wave because of the strength of the mesocyclone in this area. Okay, can we raise that up a little bit? Is there anybody in the back room? Well, Rich Thompson's name's down below Harold Brooks, and that's why I wanted to do it, because he's here today. But generally what's going on is that the storm relative winds in a high precipitation supercell situation are weak. The storm relative winds. The winds of importance in storms is what is storm relative. If the storm is moving northeast at 40 and the winds aloft are northeast at 40, northeastward at 40, then in essence, the rain, instead of falling ahead of the storm, falls close to the storm. And Harold Brooks and Chuck modeled this, and they found out that, yes, the precip falls near it, and then the strength of the mesocyclone pulls that rain around it. So that's why you get so much precip wrapping around an HP supercell. It doesn't have good ventilation to get that precip downstream of the updraft area. And you wrap it right back into the rotating updraft on the back side. And the work that Brooks et al. Did and Rich Thompson, high precipitation supercells are most likely when storm relative mid-level winds are less than 20 knots. Again, I've got to emphasize storm relative. You've got to look at how the storm's moving. Classic supercells are most likely when storm relative low-level surface state 50 winds are greater than 20 knots, and the storm relative mid-level winds are between 20 and 50 knots. Eric is looking at the same problem. He favors looking at the anvil level winds. But it does appear that it's a weakness in storm relative winds aloft that results in the precipitation configuration. And as Brooks and Doswell et al. Pointed out, the strength of the mesocyclone bears on this too. The stronger the mesocyclone, the more likely the rain will wrap around it. Looking west, one of the better photographs I've seen. Here's your updraft, your spiraling updraft. The beaver's tail, even you can see it spiraling into the storm. Heavy precip falling north, northwest, west, and southwest of the wall cloud and mesocyclone. This is your rear flank downdraft gust front extending to the south, and the strength of gust fronts with supercells is almost invariably immediately south of the center of the mesocyclone in the so-called rear flank downdraft. We're going to see there's a little bit of a difference between this and a classic supercell. You often get a clear slot developing in a classic supercell. You often have heavy rain coming around the corner on the south side in an HP supercell. And of course it makes it harder to spot. The cows are good spotters. They know what's coming. The only problem they might have is a flash flood. These storm complexes like to move along boundaries. This is a conglomeration, sort of an MCS, chock full of supercells. These are, as Ron showed last night, the older supercells kind of move to the north side of the complex with with young, very vigorous supercells near the bow. They often develop right to the right of the bow and near the bow, and then with time they transition more towards the left side of the complex. Kind of move on. This is another case. Notice this analysis came from a very careful analysis of all the data, hand-drawn. Here is a low in eastern New Mexico, a dry line, a warm front, and an outflow boundary from warning storms that have moved up the northeast panhandle. In the afternoon, some storms started developing along that outflow boundary, including the supercell that we see on radar right there, west of Amarillo, which did tornado. This is the storm complex seen a little closer. There were actually two supercells, supercell A, and we see 2 positions with it. Supercell B, we see 3 positions with it. And this is a mesocyclone right in here that produced several tornadoes, rain wrapping around them. And later on, that is a position of that weakening mesocyclone. And there may be another one developing at that point, and we'll talk about that a little bit later. The highest tops at this time were at X and Y on the leading storm flank. Isolated storms, but if you're looking at them out there, they would look kind of like a squall line type of thing. I know of chasers who've gotten in jeopardy, tremendous jeopardy, from thinking, oh, well, I can core punch this squall line. And it turns out to be an HP supercell. They don't core punch very easily. LP supercell, I'm not going to get into a lot of detail because we don't have much time. You'll see them further west in most cases. They often have skinnier, smaller towers, but very vigorous rotating updrafts. Watch out for the large hail. And on occasion, what appears to be an LP storm may produce a tornado. Just because we say that tornadoes appear to be most likely with classic supercells doesn't mean you won't get them from any kind of supercell. This is a good example of an LP supercell in 1995, looking northwest. There's not much liquid precip we can see reaching the ground. There's a little bit of discoloration in there, probably moderate rain, and there was hail up to baseball size. Large anvil canopy spreading out from the rotating storm. This is back in the action area of a classic supercell, the southwest side of the storm in this case. And we're going to look at the evolution of the rear flank downdraft. The rear flank downdraft is developing in the mid-levels of the storm and the back side of it, and it's descending to earth behind the rainy downdraft, which is up in this area. Now the mesocyclone is in here, so this rear flank downdraft area, when it finally comes to earth, starts to accelerate relative to the moving storm to the east. And a tornado is developed and moved to this point. Strong inflow on this side, strong outflow on the back side. Now the tornado is moved to this point, and it's probably in the mature stage as the rear flank downdraft accelerates on the south flank of the tornado. At this point, the question mark indicates, are there already visible lowerings on that gust front? That might indicate new tornado development at a later time, maybe just a few minutes away as this tornado matures and dies. Notice that what had been kind of an ovular or round cloud structure is now assuming more of a horseshoe shape, with some precip on radar wrapping around. Even though it looks like a clear slot in here, sometimes right at the edge of it, there is precip wrapping around the backside, and that would show up on radar if the radar is close enough as a hook echo. Now that tornado is about to lift and die. It's completely enveloped in outflow. It'll spin itself out in the rope stage. And again, the most likely area for new tornado activity to form is where that gust front intersects the pseudo-warm front boundary on the south side of the rain area. This is an area of all sorts of vorticity generation possibilities, and if a new one's going to form and we're going to have a cyclic supercell, it's usually a few miles east, east-northeast, or east-southeast of the older tornado. Here's a good example looking west out near the Texas border. Here's an older tornado. It's hard to see the horseshoe here, but a few miles east-northeast of it is a new wall cloud in the right bear on the gust front. And a few minutes later, as the old tornado's lifting, there's a new tornado already forming from that wall cloud formation. We were here looking west, the new tornado at B, the old one at A on the back side. Here's your horseshoe shape for the updraft area, with a new vigorous updraft here overshooting the top of the storm, and the old tornado dying back out here. One thing I'll be showing quite a bit of tomorrow is the horseshoe, the transition from sort of a rounded base to a horseshoe shape. Often with the first mesocyclone in a storm like this, you have it developing in the mid-levels first, and then in the cascade paradigm it develops in the low levels later, followed by a tornado. Now, we're seeing now that more and more tornadoes don't follow this, but they're more like the secondary tornadoes in this storm that Burgess did back in the early 80s. This was one of the landmark papers on cyclic supercells. He showed that you have very quick development of the mesocyclone at all depths and a quick onset of the tornado with not as much warning lead time. If you are a warning forecaster and you think you're dealing with a cyclic supercell, I tell you what, all the information in the world we have is don't lay off of the tornado warnings. Just because you see the mesocyclone weaken after a reported tornado, if you think it's or if you have reports that there's already a second tornado and you think there may be another one, don't try to time the warning with when you see mesocyclones tighten up, because there's not that much lead time. Stay with a tornado warning if it's a cyclic supercell. Don't lay off of that. Too many offices have done this, and this mistake keeps getting repeated again and again and again. They look at a decrease in the velocity, they downgrade to severe. Another tornado spins up very quickly. As long as you've got a big solid precipitation echo with a lot of reflectivity in it, and the supercell characteristics on the reflectivity hang with the tornado warnings. I cannot emphasize that any stronger. Okay, I'm going to mesocyclone and non-supercell tornadoes. What we're going to tell spotters tomorrow is don't try to call them all these terms, call them tornadoes. We'll try to tell them if it's a mesocyclone or a mesocyclone. That's not for them to try to decipher. The cascade paradigm, mid-level mesoforms. Then as Brooks and Doswell and them showed, 10 to 30 minutes later, low-level mesocyclone forms for other reasons, other vorticity sources, probably baroclinic, either coming from that pseudo-warm front in the inflow or from the rear flank downdraft. The vorticity is coming from one of those areas, maybe both of those areas in different storms. Shortly after the low-level meso forms, the tornado forms with warning lead time, if a tornado is indeed going to form. I don't know what to call the other case, so I've just called it a rapid formation paradigm. Mid and low-level mesocyclones form simultaneously or from the low levels upward very quickly. There's minimal warning lead time, and spotter reports, which are always critical, become even more critical because of the short lead time. Here's a quote from Eric that was out on our email a while ago. Visual common threads of supercell tornadoes, whether they're paradigm or otherwise. It appears that you usually have increasing spinning cloud base, a clear slot develops, tornado forms in minutes, or outflow undercuts the updraft, and there is no tornado. This is what spotters should be looking for. Now, let's see, did we have something? Oops, we had one that didn't drop, and I want it to drop. I'm going to throw it ahead again, so we'll start talking here. You still, at this point, have the first shot, there's not much of a wall cloud, a rounded base. It's the next slide, Paul, or the previous one, previous slide. That's okay, let's skip it. Let's skip it and go on. Anyway, we still have a rounded base. Here's a wall cloud. Now, one of the things I'm going to be talking about tomorrow, if you look at a wall cloud up close, it is hard to see the extension below cloud base, but it's easy to see the rotation. Vice versa, if you look at a wall cloud greater than 3 miles away, it's easier to see it hanging down, but it's harder to see the rotation. It's kind of like a spotter's dilemma. You see one or the other. Here is a well-developed wall cloud with a lot of rotation underneath a circular base, and let's watch in time. A few minutes later, it's hard to see, you've got to be up front. You know, those who sit up front in church are going to benefit. There's a whirl right there, beneath a whirl there, that's a small, weak tornado, and this is the rear flank downdraft developing. Damn. Anyway, we skipped the slide which showed the tornado forming. Now we see the clear slot working in, and we see that horseshoe shape in the updraft area. So a distinct difference here. Now this is when the mesocyclone dominated by updraft becomes a split type of system. Chuck, what did you guys call it? A divided mesocyclone structure. Yeah. So there's downdraft and updraft in this mesocyclone, and that's when it's tornado time. This was a solid tornado track all through these slides, which you're not seeing many of. Here's your clear slot, horseshoe, wall cloud, tornado. This is near Lubbock in 1978, and that clear slot gets ever larger as the tornado disappears off to the north. Okay, here is a supercell in Oklahoma. Notice it's got a concavity on the southeast side. This was a tremendous high precipitation supercell. Winds over 100 miles an hour in baseballs, absolutely devastating. A weak tornado or two. A little bit later, voila, it bows out. Ron showed some of these last night, and in looking at life cycles of, I hate to say HP supercells, because again you're going to start thinking, well, he's just talking about one type. In the storms we looked at that at some point became these HP types with a lot of precip in the mesocyclone, they'd follow one or two routes. One is where they develop into a well-developed bow echo late in their life cycle, although you may have reformation of a mesocyclone on the south flank and regeneration back to something that looks like this. But it's almost like the rear flank downdraft kind of marries into Ron's rear inflow jet with a bow echo, a little bit larger scale downdraft, and so you get a larger distortion of the radar echo late on. Of course, there's still a chance for some tornadoes near the leading storm flank. The other type, which appears to be more conducive to tornadoes, you would be tempted to say that mesocyclones are rotating around the storm. That's not really what's going on. There's a new one developing here, And that's responsible, I think, for producing most of the precipitation falling here, whereas this is a weaker updraft and maybe more rotation than anything. But in this case, there was an F4 tornado on the ground there in Palestine, Texas. And we've seen a number of storms that look something like that. Now, usually the meso is weakened by the time it gets to that position, but in this case, a tornado on the northeast side of the storm. This later produced another F4 tornado in the more classic position on the south flank of the storm. This is another storm we looked at, similar to these, with greater detail and with Doppler this time, with the 88D. This was a January storm, an elevated supercell near an 850 millibar triple point. The air temperatures at the surface were 45 to 48 degrees. We don't know of any tornadoes, but this thing produced hail up to grapefruit size in January. It was a very rude awakening for a lot of people south of Dallas during the AMS conference in 1995. I've got to think the meteorologists had something to do with that. What we found is that this is the flanking line in here. This is the main updraft area. This is where mesos would start developing in the mid-levels. They would deepen and strengthen at this point in the notch. And then they would expand and diminish up in the precipitation area. This is where the big top is on the leading edge and the maximum overhang. But there would be another top a little bit offset from the reflectivity core in this area, indicating probably a little updraft aloft, maybe associated with that rotation. I don't know. But these things would develop every 10 or 15 minutes and roll right up the complex as the complex moved to the east-northeast. What does a storm like that look like? This is not that storm, but it's one that's similar. This was in southern Kansas. The storm was moving east-northeast at 40 to 50 miles an hour. It's roaring at us. We're roaring to stay ahead of it. We turned and looked at it at this one point. There is a tornado warning. Now, you tell me, from what you've learned, I'm going to go from left to right. You tell me where you think a tornado would form in this storm. Just speak up when you think so. Yeah, the wraparound area, right? Certainly. And that's probably the case, but we're seeing a lot of tornadoes developing from the bow on up into that area. And I'm going to show you an example of that. There's a beaver's tail back in there. This storm had the strongest low-level convergence I've ever seen. We could hardly stand up in the east winds, 40 to 50 blowing into the storm. And we hit the outflow once, and the winds were about 40 to 50 on that other side. Diametrically opposed, 180 degrees, coming right at each other. At one point, and I didn't understand, I was completely baffled by it. At one point, I saw at Cloud Basin here a strong rotation. There. And I said, what the hell is that doing there? That ought to be anticyclonic or nothing at all. Remember the last slide we just looked at? Development area down here, moving north with time. Apparently there was already cloud-based rotation with the next mesocyclone here, and that probably got back in here. There was a reported tornado about 20 minutes after this, somewhere up in there north of the road. We could not get to that part of the storm, unfortunately. Here's another storm looking west. Yeah, it doesn't look like much. I was mobile with Sam again in this, and he looked at this and he said, do you think that we might get a tornado in the front flank? And I said, hell no. It's not going to happen up here. Next view, we're looking northwest. Looks like a squall line type of storm, kind of a shelf, kind of a rounded cloud in there. That's about 4 miles from us. Now, Gary Woodall, who works in the regional office in Fort Worth, was north of us in the next road. That's the same cloud we were just looking at in the last slide, right there. Looks a little more isolated from his view. Further, look at the horseshoe. See it? There's your horseshoe. What we've got is an older decaying mesocyclone in here and a new one developing right out on the bow. And there's your tornado looking due north. Front flank, and the rain was starting to wrap around it, and it disappeared from our view. We didn't have a good viewing angle. Here's your radar echo. We were here looking north. The tornado was right there. You can see it's not a true bow echo, but that part of the gust front with this HP supercell was bowing out, and that's where the tornado was, right there. Not back in there, but right there. There was just recently a paper from the Sioux at Tulsa on the Fort Smith storm. Apparently what threw them is, it's a pretty good shot from Tulsa with a Doppler. They had a meso in there, and the Fort Smith storm occurred out there on the bow. So they were a little confused as to what was going on with two mesos so close to each other. And we've got a storm here that's probably rather similar to it. This is in a line, and that brings up another mechanism Eric has talked about for getting an HP storm, and that is, there's another storm behind this we can't see. Maybe seeding from that storm is helping this storm produce sort of an HP appearance. You remember that one slide we showed of if the updrafts line up, they drop rain on each other. This out here, the reason I mention this, this is a classic supercell that's about the tornado. Classic HP. It's hard to see, but that's the storm we just looked at, the tornadic storm. On the front flank, there's a beaver's tail, and the high top with overhang is right in there in the front flank, and that's where the tornado was in there. This is looking north. Here's another line. Let's play a game again. I'm going to go up the line, and you tell me where to stop, where you think the big trouble is.
Right there.
Okay, that looks like some trouble possibly. Maybe in there.
Oh, there.
Okay. Well, there probably were several areas of trouble in the woods we'll never know about. We had several severe thunderstorm warnings out, but the oddball thing is this thing in here is the hot spot. The radar is right over here. When this squall line was west of us, it was a little more broken, and we had two mesocyclones in the mid-levels that never did work down low. Then it got right into the RDA above the radar, and we got a report of a tornado on the ground. Now, we weren't going to wait any further, you know. Man, we put out a tornado warning for Dallas County. Luckily, there was minor damage. That thing there produced 6 tornadoes in Dallas County. 6 small ones, fairly weak. There is that little thing. There's your bow. And earlier, there'd been a mid-level meso up with this thing. There was not at this time. No mid-level meso. But there's your mesocyclone in the low levels. Radar's back in there, right over Lancaster again, guys, the year after the Lancaster storm. Sam Barraclough went over and surveyed, and he found 6 vortices in Dallas County, all of them F1 to F2. One was a minimal F2. This is the lowest scan. It's at about 2,000 feet, a good tight little meso. Now we go up just a little bit higher than that, and what do I have marked on there? 10,000 feet, nothing. Just some inbounds and outbounds. That's inbounds coming over the top of the gust front. That vortex is less than 10,000 feet thick. That series of vortices. Okay, let's play that game again. There's a gust front, right? There's. Damn, y'all are ready to do warnings. This whole area produced 60 mile-an-hour winds, but the winds here were over 100. Didn't show up on this was base velocities, I think it was. And there's that outflow boundary. Notice one thing that I've seen over the years, and other people have noted. Notice how these echoes have gotten strung out here. Often where there's strong outflow, you see that the precip in the low levels get strung out parallel to the strong outflow. But these winds here were marginally severe. It was in this area where the real nasty stuff occurred. Never could see a clear meso in there, but there's a lot of cyclonic shear. 100 mile-an-hour winds. The May 5th storm, how are we doing for time, Paul?
Another 5.
Oh, wow, we're doing great. Squall line back out to the west, small isolated complex developing in here. And I looked for my surface chart, couldn't find it, but there is a strong sort of a mesoscale cold front with a squall line back here and a very strong mesolow on it with intense pressure falls over the metroplex at this time. Bad stuff. This is what the people in our office didn't catch late afternoon, but Mike Foster did catch this guy developing, and he didn't like the looks of it. It looks rather multicellular here. That did not last long. Now it's starting to get that concavity. It's looking pretty tough. Let's look at it in time. Here's a 4-panel. It's over in Parker County, just west of us. This is 0.5. I think this is 2.3, 6, and 14.6. Notice these 2 roads right here, and there's your hook. And what we see in this clear area here is this. That is all overhang, way out like that. About 8 to 10 miles of overhang. Oh man, they're about to get, again, a tremendous shot of hail from this. Now it's got that quintessential supercellular look, wrapping hook. Here's the squall line behind it, which is trying to catch up. And it's starting to. It blows out in this location. And at this point, I don't have it today, but one of our spotters who's become a chaser, Bobby Edens, has a beautiful nighttime, about a 3-minute video of that mesocyclone becoming rain wrapped. Beautiful video. It's very vivid in the lightning. Wish I brought it. I did not. Here that hook is wrapping up, and a little bit later, it's all wrapped up in the storm, and another cell develops on the south flank, also with a mesocyclone. There is one hail swath in here, unbelievable hail going into downtown Fort Worth, stretching on out into the county back out to the west in here, and tremendous hail damage. The Mayfest Outdoor Festival was struck, and about 130 people were injured by hail as they were trying to flee the area. Luckily, nobody died. At this time, grapefruit hail in downtown Fort Worth. At this time, softball hail in Wedgwood with that cell. Another hail track, another hail streak. And here's a closer view of the storm in downtown Fort Worth. There's the Wedgwood cell. Again, new mesos developing on the right flank and moving into the heart of the precip area with time. And look at the B weir. That is a huge B weir up at 19.5 degrees, about 15,000 feet. Very close to the radar. And as the storm moved off, another 4-panel, low levels, mid levels, and in the upper levels, 2 tops. One with the old precip area and another which is with the new overhang over in this area. I would say that this is probably one of these storms. It's not quite like that. This is more into somewhere between the strong and weak evolution for new cells in the flank. It's a multicell supercell. But it's a supercell, obviously. That's the important thing. Squall line catches it. The hail diminishes. Now, what have we heard before about squall lines catching supercells? A Huntsville tornado? Well, in this case, the guys in our office were worried about tornadoes, and they put out another tornado warning for Dallas County. The next thing they knew, all of a sudden they were getting reports of people being killed in flash floods. 1 or 2 reports, they put out a flash flood warning, and for the next 30 to 40 minutes, people continued to drive into flooded areas and get killed. They disregarded the flash flood warning. And there's still a circulation there. We can see it quite evident in the reflectivity. Probably a large, lazy circulation at this point. Rainfall rates in this storm at this point were 3.5 to 4.5 inches of rain in 30 minutes. Now, we've had a number of storms like this go over the Dallas-Fort Worth area. You won't read this at the back, and I apologize. These are 8 of these giant supercell storms that have come across the Metroplex. 4 of them produced tornadoes, 4 out of 8. I feel like when I see one of these coming, that's enough justification for me to put out a sneaky tornado warning. Whether I think it's going to tornado or not, and these tornadoes that occurred, and most of these were kind of superfluous to everything else that occurred. But I've got to grab the public's attention, and I'm not going to do it with a severe thunderstorm warning. What I subscribe to is a dual tornado and flash flood warning for a storm complex like this. These are the deaths and injuries: 20 and 120, 0 and 30, 0 and 7, 6 and 29, 2 and 14, so forth. The damage: 1.5 billion, 220 million, 600 million, 100 million, 250 million, and back in the Stone Age, a little bit less. The hail size, max hail, 4 inches in diameter, 3.5, 4, 275, 3, 4, 4.5, just little bitty baseballs here. Winds, max winds reported. Some of these are estimates, but where I've got 120, that's because steel transmission towers were knocked down by outflow. And that happened with 2 of these events. And rainfall rates, some with question marks, 5 inches per hour and up. And I've been conservative on those rainfall rates. Some of them are really 30 minutes, 4 inches, 8 inches an hour. This is nasty stuff, and you've got to be ready for this kind of thing. Very quickly, a couple slides. Here's a hook echo in a little line, but that's not where the tornadoes were. They were here. And right between, let me get to the right slide. I'll just skip over here. This is the right slide. Here's a close view. This is Greg Stump's April 19th, 95 storm. It almost looked like there were two pieces of echo, one there and one there, and a weakness in between. There's a strong gust front in here, as we see over there. If you look carefully, there's tremendous convergence on the gust front. The radar's down here, looking in that direction. Tremendous convergence. There is one little circulation. There is 2, 3, and 4. And 4 up here is out in this area where that hook echo was in the lower elevation scan we just looked at. Behind the storm, that's where a hook was showing. Several circulations. The genesis appears to be right on the gust front near the bow again. And finally, here's a B weir as it comes in towards downtown Fort Worth, and a tremendous circulation, and an F2 tornado developed minutes later. That was about a 50-knot circulation over about 3.5 or 4 miles, I think. Right on in here, not where that old hook was showing up earlier. Strange stuff. We're seeing a lot of new stuff now. Likely areas for supercells. This is from a master's thesis I did 20,000 years ago. Near surface lows and dry line bulges, and thermodynamically between the hot air behind or on the dry line and the moisture. Notice I've got a tight gradient of temperature. That probably represents boundaries in most cases. And I subscribe to what Eric says. Usually you've got boundaries out there of some sort when you get tornadoes. Gerald, to close it up, just a couple of slides. So here we are. People have analyzed this as a front, but and go back and read Chuck's paper that he did with Sanders on frontal analysis. This is the front. This is a prefrontal trough, probably yesterday's dry line garbage. And here's a triple point low near where they intersected. Old thunderstorm outflow boundary northeast Texas, kicked out a ripple of some gravity waves. Some people say that triggered the storm. I don't think so. I've got my doubts too, like Chuck. I think other processes led to the development of that thing. I think that was just incidental, but we threw it in. And some satellite photos. There's your thunderstorm complex in northeast Texas, prefrontal trough, cold front back in here. There's your storm developing near that small triple point low. The triple point low moved right down that boundary, that stationary boundary with the storms. The cell development on the flank, the propagation took over here. The winds aloft were fairly light. The storm never did get blown off of the boundary, but the new cell development dominated, and so the cell moved southwestward, as did the tornadoes. Here's the storm moving along, a well-developed flank, moving to the southwest. And a little after Gerald was struck, it's a huge storm, another large one down near Del Rio. These are the 10 tornadoes we know of, 11 rather. There's an 11th right there. Here's Gerald, F5, the Lake Travis tornado, F4. And here, this is about 20 minutes before the tornado strikes. There's a hook at 14.6 degrees. Can't see it, I'm sorry, but in the same area there is a mesocyclone aloft. It is a supercell. And I'll skip that. And it's a little hard to read these. I do apologize. But there is a TVS, shows up right here and right here. And that's the Gerald tornado, right in here. Supercell ingredients, moisture and stability, lift, favorable vertical wind shear. Supercell tornado ingredients, moisture and stability, lift, favorable vertical wind shear, and whatever it takes. Eric will be talking about that. I was going to show the Gerald video, but we'll have to look at that tomorrow because we've got to eat lunch. Thank you. We'll look at the video right after lunch. Is that okay?
Before you go, I'll tell you what. Mike Blackwell, are you here? Those of you without banquet tickets or without lunch tickets, stop at the back desk. There should be.
Well, that's what this is supposed to be about. Yep. Yeah.